Okay, so this will be the first topic of for the first kind of area for the second topic of Unit 2. One thing to know is that Unit 2 is broken up really into two things. There's one giant heading called Dynamics. Okay, so what you see right here, that Dynamics, where we're taking motion and combining it with forces and seeing how they relate. Okay. The first topic just really focused on Newton's first law, Newton's third law, and how we draw free body diagrams. Now we're going to get into Newton's second law of motion, and then how we bring it all together with problem solving and so forth. Okay, so recall that Newton's first law of motion explains what happens to an object that has no net force working on it, right? So all the forces are balanced, or we say the object is in equilibrium. Okay, so remember, that is Newton's first law. All right, now what's going to happen is his second law of motion, right, is going to answer the question of what happens to an object that does have a net force acting on it. Right, so what really happens is this law will re-identify or redefine acceleration. In fact, that's the connecting piece between dynamics and forces, is acceleration. Okay, that's very important because the acceleration that we're going to determine here using forces is also the acceleration of an object. Okay, so the second law, Newton's second law of motion states the acceleration is directly proportional to the net force acting on the object and inversely proportional to the mass of the object. Okay, so this is, if you kind of look at it in a first law sense, right? Well, there's no net force acting on the object, hence there is no acceleration on the object, right? So that's when we're talking about the different types of equilibrium. Another way to think about his second law is that it is Newton's mathematical law. This is the law here with motion, excuse me, that has a mathematical formula with it. Now, by definition, by what the law states, it's again redefining acceleration. So the acceleration of an object is directly proportional to the force and inversely proportional to the mass. But in fact, this is the net force. So let me kind of rewrite this a little bit because we're looking at net force, we're looking at the sum of the forces, and that's what that little, so this here is the Greek letter sigma, okay, and mathematically it just means to sum. One thing you do need to note that in physics, sum means really to subtract, because what happens is we have positive forces, we have negative forces. Well, when you really add those together, you're really subtracting, okay? But we write this law linear, right? We don't want to be on two separate planes. We don't want a numerator and denominator. We don't want to write it as a fraction. So we write it linear, and we just say the sum of the forces equals mass times the acceleration, okay? And so this is this sigma F, remember, excuse me. So remember, sigma F is simply the net force. Okay. So again, just to remind yourselves that the SI unit for force is newtons, right? Named in honor of Sir Isaac Newton. Understand that this is not mass, okay? Because if we look at it in terms of weight, right? Weight is given to us in forces. Weight is a force, mass is not. So here in the United States, our customary unit for forces is actually pounds. So when you go to the doctor's office, they tell you how many pounds you are, they tell you how much you weigh. If you interested in mechanic, like being a mechanic, they'll talk about PSI. That's pounds per square inch. Okay, and we'll get into that. That's pressure. So the conversion factor is 1 pound is equal to 4.45 newtons. Okay, that is the conversion factor. Okay, between the two. So let's look at an example problem. Just a quick example on how we use this equation, right? Or here's a couple actually, focusing on Newton's second law. All right, so this is Moe, Larry, and Curly push on a 752 kilogram boat that floats on a dock. I forgot the word, the letter K. We're talking about a boat dock. Okay, so they each exert an 80.5 Newton force parallel to the dock. What is the boat's acceleration if they all push in the same direction? And then what is the boat's acceleration if Larry and Curly push in the opposite direction? Okay, so if I have my boat, I have what I need to do is find the net force acting on this boat from Moe, Larry, and Curly, and then I can find the acceleration. Okay, so I've got 3 forces, right, all headed to the right. They all have an 80.5 Newton magnitude. Okay, and I'm asked to find the acceleration. And it's a 752 kilogram boat. Okay, so all I have to do is really the sum of the forces is equal to mass times acceleration, or acceleration equals the sum of the forces divided by mass. And so what I really have, the sum is just 80.5 times 3, because I have 3 of the same forces, divided by 752 kilograms, okay? And that'll give me the acceleration if they all push in the same direction. So a quick calculation, we find that it has an acceleration of 0.321, or 32 meters per second squared, okay? Now, what happens if 2 of them are now pushing against, right, the grain, right? So we have 2 heading to the left, and we still have we still have Moe pushing to the right. Okay, so if you ever watch the Three Stooges, this often happens, right? Where one's trying to do one thing and the other 2 are doing their own thing. Okay, but again, physics-wise, we do the same thing, right? Still a 752 kilogram boat. And we're still asked to find the acceleration, okay? So when we do the sum of the forces now, so note that this is positive because we're pushing to the right. So now we're going to do the sum of the forces. Now let's find it separately. So we've got 80.5 to the right, but then I got 2 80.5s to the left, okay? Which this 80.5 cancels one of those, which tells me I have a net force of 80.5 to the left. So basically what happens is Moe's cancels, let's say Larry's, right? And now we can find the acceleration by just simply doing the sum of the forces over the mass. And we know that the sum of the forces was negative 80.5. We're going to divide that by 752. So 80.5 divided by 752, and we get an acceleration of negative 0.11 meters per second squared. So what you can really see here is that it's essentially one person pushing this boat, because Larry and Moe cancel out, leaving just Curly pushing the boat. On the part A, right, so all 3 pushing together, okay, that's why the boat has a greater acceleration, okay? All right, next question says the 2 groups of canoeists meet in the middle of the lake. After a brief visit, a person in canoe 1 pushes on canoe 2 with a force of 46 newtons to separate the canoes. The mass of canoe 1 and its occupants is M1, which is equal to 150 kilograms, and the mass of M2 is equal to 250 kilograms. What is the acceleration of each canoe? And what would happen to the acceleration of canoe 1 if the mass increased? And then what happens if it would decrease? Okay. All right. So let's start with the first question, right? So what is the acceleration of each canoe? Okay. So for canoe 1, right, the force is going to be, and we'll call, so these are our canoes. Here's one, here's two. One pushes this way, right, to the right, which means one's going to travel to the left, two is going to travel to the right. So two will travel positive, one will travel negative, all right? So what really happens is so the person in canoe one, albeit they're pushing on canoe two, they're actually going to go backwards in accordance with Newton's third law, right? So we know that the acceleration is going to be the sum of the forces over the mass, which means it's going to be negative 46 newtons divided by 150 kilograms. So 46 divided by 150 gives us negative 0.31 meters per second squared. Okay, for canoe two, we can kind of predict what happens. They're going to be heavier, right? So the canoe two is heavier. They're 250 kilograms, which means they should have a smaller acceleration, right? So again, now they're going to have acceleration in the positive direction because they're going to the right. So it's going to be 150, 46, positive 46 divided by 150. Oh, sorry, 250. They're at 250. And so we get an acceleration of 0.18 meters per second squared, okay? In terms of magnitude, it is definitely smaller, right? But just in the opposite direction. Now, the next part, or the next question, what would happen to the acceleration of canoe one if the mass increased? So we can kind of see what happens, right? So canoe one, right? If mass goes up, right? Think about those relationships. So if I increase my mass but keep the force the same, the acceleration has to work opposite. So it's going to go down. Okay? Now, for the second question, what happens if the mass decrease? Right? So if mass goes down, remember, mass and acceleration work opposite of each other. They're inversely proportional. So if one goes up, the other goes down. But if one goes down, the other one goes up. And you could, if you want, you don't believe it, go ahead and do a quick calculation, right? Canoe two could be where the increase of mass of canoe one, but then go ahead and decrease the mass of, or excuse me, the mass of canoe one to 100, and you'll see you get negative 0.46, right? So you can see that the acceleration would go up if I decrease the mass, right? So so that is just some basic stuff for Newton's second law. And just using some, some of the basic problem solving, right? These questions are relatively easy because the mass and the force and the acceleration are all in one direction. But in the next video, we're going to address some problem solving when you start getting all kinds of craziness when one, they goes in opposite directions, or one goes vertical, the others go horizontal. Okay, and that's going to be a little bit more of a process.